Alright guys, in this video we'll go through the formal test, carrying out a hypothesis test for the goodness of fit test chi-square. In our last video we went through the procedures of the calculation for the chi-square test statistic and the conditions for that test. The conditions for the goodness of fit test are random, and it's a large sample condition, and then independence. And the large sample size is that all the expected counts are at least 5. And because it's a multiple comparison test, we've lowered the threshold for expected counts or predicted counts. What used to be 10 for n times p in the one prop test, because we're doing multiple comparison, we lower the threshold and say that effectively those NPs only have to be 5 across the board to follow the chi-square statistic, or the chi-square distribution. The independence check is that if we're sampling again without replacement, that it's our 10% rule. So this is for an SRS. We want to make sure that the 10% rule is met. And then otherwise, that it's a random sample or randomized experiment, random assignment. So those conditions are what allow us to carry out the test. The test then would consist of the null and alternative hypotheses, which can be written out as the data does follow the distribution stated versus it does not follow that distribution. Or you can write it out as all the p's are equal to their corresponding proportions stated in the hypothesis versus at least one of those p's is incorrect. So either of these is fine. The statistic itself is the sum, as you may write it this way, the sum of each observed minus expected squared over the expected, which is fine. And then the degrees of freedom is k minus 1, where k is the number of different categories, not n minus 1. It's the number of different categories minus 1 for this distribution. So we'll go through a couple examples to get you prepared to work on the homework problems. The first one here says we've got 140 births, that's n. And let's see, do they give significant evidence that the births are not equally likely on all days of the week? Effectively, that's our alternative hypothesis. So the null is that birthdays, birthdays, I guess, in this area are evenly distributed across the week, across the days of the week, versus the alternative that the birthdays in this area are not evenly distributed. So that's one way of writing the null and alternative hypothesis. Given that we said equally likely and there are 7 days in the week, it could be written this way, and I won't do this for all the examples, but just for this one. P sun equals P mun equals ... equals P sat, all of which equal 1/7, versus the alternative that at least one of the proportions is not equal to 1/7. And you want to be sure that you define that P sub I equals the ith day of the week proportion of births in this area. So not only do you define it, but, well, if you're going to write it this way, in terms of P, the proportion, you need to define what P is. Otherwise, you just write it out in words as it fits the distribution. You're not defining a parameter in the first set of hypotheses there. We weren't told, I don't believe, so we'll go with alpha equals 0.05. If the conditions are met, this is the chi-square goodness of fit test. And you're going to have to say goodness of fit because we're going to have other chi-square tests. So very specifically, this is the goodness of fit test. So we'll say, okay, random. You really want to say normal and independent, but it's large sample size. And again, it's not normal because it's very specifically the chi-square. It's not a normal distribution. And independent. So it was a random sample. SRS was stated. We'll go ahead and put that in there. All the expected counts. So it's not the observed counts, which are these values in the table. That's what they observed. But we need all expected counts greater than or equal to 5. Now, in this case, because we have 140 in our sample, and that's n, and 1/7 was the probability of success. So we expect 20. If they are truly evenly distributed, we need 20 births each day, and all those expected counts are greater than 5 because they're all 20. And then independence, we're assuming that the random sampling from a finite population, that 1,400 births in this area is reasonable. And, no twins or anything like that. So once the conditions have been met for the chi-square goodness of fit test, which you can either, again, write the name or chi-square equals the sum of each observed squared over the expected. You can write it either by name or by formula. Then we're going to come down and do the work. So to show the calculation, because it's a sum, you do not need to show me each component, but I'd like to have an understanding that you know what's going on. So I'm going to write the first component here. So this represents, if we get it in there, Sunday. So there were 13 observes minus 20 expected. We take that difference, we square it, divided by the expected. Remember, all the expected values are 20. So that's the first. And I could write all 7 of them, but I'll save everyone some time. And we're going to jump straight to the last one, which was Saturday. And there were 15 of those. So it's the sum. You start at the beginning, go to the end. That's enough for me. And either, you could do it using your lists on your calculator, or really knock it out by hand, or use the goodness of fit test on your calculator, but you should get a chi-square statistic of 7.6. And there's a separate video showing you how to knock that out on the calculator if you want to check that out. So we would take this value and look it up either on the table, or if we've done it on our calculator, we could get all the information from there, which is fine. But I still want to see the work that's been done. Degrees of freedom equals 7 minus 1, so number of days or number of categories, minus 1, which is 6. And if we look at our table, this chi-square value doesn't even make it onto the table. So we know that the p-value, the best we can say, is that it's greater than 0.25 based on this 7.6 for 6 degrees of freedom not even making it onto the table. Right? It's too small. And smaller values, chi-square values, mean better fit. A perfect fit would be a chi-square of 0. This is a relatively small value for 6 degrees of freedom, so we're going to end up with a pretty large p-value. If you were to use your calculator, you could either run the goodness of fit test if your calculator has it. A lot of calculators have chi-square CDF, so you could find the area where 7.6 was a minimum, and you pick some arbitrarily large maximum value for 6 degrees of freedom. And it turns out to be, from the calculator, about 0.269 as the p-value. In either case, the p-value is greater than alpha, any reasonable alpha, therefore we fail to reject the null hypothesis. Okay? The sample does not enough evidence to say that, all local births in this area are not equally likely. Across the days of the week. And you can wordsmith that however you'd like, but we do not have evidence to say that they're not likely. We're not confirming that they're equally likely, of course, but we just lack the evidence to say that they're not evenly distributed. So if you're feeling pretty good about this, then go ahead and start trying the homework problems. If you want another example, I'll post another video.